Good morning. We are moving on into chapter 25. So we're getting more and more into the physics of kind of practical electrical sort of stuff. So how do we use electrical energy when we plug something into an outlet, or we put some batteries in something and we run that device? What do those circuits look like? And so in chapter 25, we are going to introduce electric current and electric resistance. Now, we've already sort of been talking about electric current, so let's take a look and see what this chapter is going to consist of. And then also I want to point out that we just did a chapter on capacitance and capacitors, and so that's already kind of a lead-in for electric circuits. But we're going to move farther into that in this chapter. So here's a battery, and we've talked about this before. Here's a battery. It's got a positive terminal, it's got a negative terminal, and the battery runs a chemical reaction. So there's some kind of chemical reagents inside the battery. There's a reaction that's going to be running in that battery, and the result of the chemical reactions is going to be to remove electrons from the positive terminal and place electrons at the negative terminal. Now, did I put a switch in this circuit? Oh, I've got to remember to put switches in. So let's say we have a switch and we open it up. Well, when we have the switch opened up, the progression of electrons through that circuit stops. It shuts down. When we close the circuit, and by closing the switch, then what happens is we have a complete path. And then the electrons can begin to go back into motion. Now, as we talked about before, a lot of people have kind of an idea that electricity moves super fast. Now, electrical effects happen pretty quickly. If I hit a light switch, the light comes on immediately, pretty much instantaneously. That doesn't mean, though, that the electrons are actually traveling instantaneously. So what's happening is, as we've talked about, the electrons are present in all parts of this circuit. And when I close the switch, the battery begins pumping the electrons. All the electrons are lined up with other electrons. And the model that we introduced was to say that electrons are not easily compressible. Electrons are kind of taking up enough space that if one electron begins to move, other electrons are affected by that immediately. So in order for these electrons to continue being pumped, well, all these electrons throughout the circuit then are making their way through that circuit at some speed. Not, in most cases, it's not a very high speed. But what happens then is we don't need the electrons from the battery to reach the electrical device. There's already electrons over there. So our description here was to say, it's kind of like having these electrons move through the circuit. It's kind of like lining up a bunch of blocks, where the blocks are the electrons, and then we push on all those blocks, and the blocks push on other blocks. So we don't have to push all the blocks individually. We're just going to pump electrons where the battery is located, and that's going to set all the electrons into motion through the circuit. Now, we're going to introduce in this chapter a property called electrical resistance. Now, resistance, we're going to use a symbol for this. We're actually going to have electrical devices that are designed to have a specified amount of electrical resistance. And we call those, surprisingly enough, we call those resistors. And so our resistors are going to have a property of resistance, and they're going to have some number of ohms of resistance. That's the unit that we're going to be using for the resistors. So ohms are going to be the units that we're working in terms of. Now, if that's resistance, what is electric current? Electric current is the flow rate of the charge through the circuit. Now, what we've just talked about, these electrons making their way through the circuit, how would the flow rate here compared with the flow rate here and the flow rate here and the flow rate here. And if we're understanding the properties of how electrons are moving along, the flow rates are going to match. So it doesn't matter where in the circuit I go in and measure or imagine making some determination of what the flow rate is. The flow rate here and the flow rate here and the flow rate here and here and here and through the back, they're all going to match. Because electrons aren't going anywhere. Electrons are conserved particles. And so we're putting them into motion, and for every electron that passes a boundary right here, we need to have another electron passing a boundary here. Otherwise, the electrons are going to build up. And there's no place in the circuit where the electrons are building up except for the capacitors. And so the flow rate of charge is going to be the same everywhere in that loop. This is just a one loop circuit. Now, more complicated circuits could have different flow rates in different branches. But if I'm looking at just one specified path that the electrons are following, everywhere along that path, the electrons are going to have the same flow rate. Now, the current then, surprisingly, the symbol we use for current is I. So I represents electric current, and current is defined as the rate at which charge is going by. So if I stand, oh there I am, if I stand right there and I draw a line in the circuit and I get out my timer and I measure the charges going by, if I take the rate for every dq, or for every time interval dt, how large is dq, that tells me the instantaneous current. If I have kind of a steady flow rate going by, then I could calculate the current by allowing some amount of time to go by, calculating the current, and then taking the amount of current, dividing by the time, and that will give me a current or an average current for that time interval. Now the units for electric current then would be coulombs per second, and those are referred to as amperes or amps. So the symbol there is a capital A. I didn't write it. I guess it needs to be written down somewhere. But those are going to be in the units that we call amps. And everybody's heard of voltage. I'm guessing everybody's heard of voltage. That's really familiar. And then a good number of people also, you hear the word amp. An amp is specifically referring to this flow rate. So voltage and amps, voltage and current, are two quite different ideas, okay? So voltage, or electric potential, is related to how much energy the charges have, and the flow rate, or the current, is determining the rate at which the charges are moving through the circuit. But if I take the voltage and I multiply it by the current, that's going to give me a rate at which energy is moving through my circuit. Okay, and we'll get back to that on the next slide. Right now what we want to do is say, for this particular circuit, what determines the flow rate? So back when we were looking at mechanics in Physics 4a, we said that the acceleration depended on the force divided by the mass. Well, this is kind of a similar idea. The flow rate depends on how energetically the charges are being pushed by the battery. If I have a higher voltage battery, those charges are coming out with more energy. So more voltage will drive more charges, or drive charges at a faster rate, some combination of those. And the resistance is actually what slows things down. So resistance corresponds to how often do the electrons run into things. It's kind of like friction. If the electrons are running into things more frequently, then they run into something and then they have to be pushed some more. So just the same way that if there's more friction, more resistance, electrically, if there's more electrical resistance, then the electrons have to be pushed with additional forces. We have to put more energy into the circuit to get through that additional resistance. And so the current then is going to depend on voltage over R. I just made up some numbers here. I made up an imaginary 40-volt battery, and I made up a resistor that was 20 ohms. Now when you think, well, yeah, what's a resistor? I don't plug a resistor in, do I? Well, a lot of devices actually are basically resistors. So this light bulb right here that they started off with, that filament is a resistor. So most of the resistance in a circuit that has a light bulb in it, if I plug in a light bulb, the light bulb has quite a bit of resistance compared with all the rest of the wiring, and that's the part of the circuit where the energy ends up and the light bulb lights up. Other devices that are just resistor. What about a toaster, right? If I want to toast some bread or something, a toaster is just kind of a resistor. It's a region within the toaster that heats up, and that's where the energy primarily ends up, is going into heating up that resistor that we've got. So those are examples of fairly simple devices that we use that are basically just a resistor. Any kind of a heating element, maybe it's a clothes dryer, if it's an electric oven. We could have heating elements within the electric oven or the electric range that are generating that thermal energy. All right, so this, if you notice, we've really highlighted that formula. That is really one of the fundamental formulas when we start looking at just electricity use. So, you guys could get maybe your electrician's license or something after taking this class. All right, the second formula, we said that coming right up was this formula of power. Power is energy per time, and energy, we've said, is charge times voltage. That's what we've seen back in chapter 23 when we were looking at electric potential. And so if we take the number, we take the amount of charge times the voltage they are being driven with and divide that through by time, that will tell us the rate at which energy is going out into the circuit. And if I have a circuit set up with a voltage of V and it's generating a current I, that product tells us how much power. And so where is the power going in the circuit that we have set up? Well, the power is coming from the battery. So the battery is providing energy at some rate. Some number of watts are being provided by that battery. And in this circuit, the energy is going into the resistor. So notice that the voltage being provided by the battery is also the voltage across the resistor. We see that the battery is maintaining a certain voltage or a certain energy difference across that resistor. And that means that the electrons are going to end up releasing their energy, making their energy available. The electrical energy that we've given them is now going to go into heating up the resistor, for example, if that's the device that we're looking at. So this formula applies to the battery. The battery is providing the power, and it also applies to the resistor. The resistor is using that. The units for power are watts, so that hasn't changed. That remains the same as what we saw in Physics 3A. Okay, what about resistance? If we design a device with the intention of having a certain amount of resistance, what's that going to depend on? So it turns out the resistance of our resistor depends on what we make it out of. There's a material property called resistivity. Symbol here is rho. And for copper, for example, copper has a really relatively low resistivity. Copper has a resistivity 16.8, 10 to the minus 19 ohm meters. And so the resistance of a device depends on the resistivity of the material. It depends on how long the resistor is, and it depends on the cross-sectional area. So if the resistor is twice as long, it's going to have twice as much resistance. It's twice as much distance that those electrons have to make their way through. If it has twice as much cross-sectional area, then that frees up the electrons to travel not as fast through the resistor. There's more lanes available, and so the electrons are more easily able to get through, and that reduces the overall resistance. So it's a fairly simple relationship. It's what the material is times the length of the resistor divided by the cross-sectional area. Now the resistors, I think we'll see this in the next slide in more detail. If you open up an electrical device, you'll probably see that the resistors inside there, they tend to be these cylinder-shaped devices, and they have these bands of different colors on them, which are kind of a code for how many ohms of resistance those resistors have in them. Okay, let's think about power sources. So where are we getting the energy from? What's providing power for us in order to operate a circuit? Now, the energy sources, or the power sources, or voltage sources, are batteries and generators. I want to put those in, I mean, for the most part, either we're running something off a battery. Now, if it's a battery, there's a chemical reaction running inside the battery, and that's what's providing the energy. Now, a battery provides what we call, well, direct current, the voltage as a function of time. If we look at the voltage as a function of time, if it's a 1.5 volt battery, then it just maintains that 1.5 volts, right? So the voltage here would be a constant, and that provides what we call direct current. They don't call it constant current or constant voltage. They call it direct current. Okay, so that's just what it gets called. So that gets referred to as DC. Now, when we generate electricity in a power plant, it's not a bunch of batteries. It's not a bunch of chemical reactions running. Power plants are driven by mechanical devices. What we do is, within a power plant, is we're able to take a bunch of wires and move them through a magnetic field. We'll see more of this in some later chapters when we get into, well, 27 and 28 we'll be looking at magnetic forces and magnetic fields, and then in chapter 29 we'll look more specifically about how AC generators operate. But the power plants that we work from are generating what's called alternating current. It turns out that it's more efficient to transfer energy from the power plants through the electrical power lines. It's more efficient to do that if we alternate the voltage. So instead of trying to produce a nice steady voltage, we actually produce a voltage that alternates. Now it turns out when we're spinning the generators, that's a pretty easy thing to do, is to spin them in a fashion where the voltage is varying, well, like a sine or a cosine function. A cosine or sine function can be used to describe the orientation of the generator as it's rotating, and then the sine or cosine function can be used to describe the voltage that's being set up inside our generators. And again, we'll see this in a few chapters. So for the direct current, for the batteries, we're going to get this nice steady voltage, whereas with the generators, the stuff that our outlets are connected to, the voltages here are going to vary like a sine or a cosine function. Now, how do resistors respond to this? Well, we can still use the equations that we wrote down. We can still use the equations of the current, whether it's a direct voltage or alternating voltage. The current will follow whatever the voltage is doing. So for a simple circuit where we just have resistors and a power source, The current, if the voltage is varying like a sine function, the current will vary like a sine function. If the voltage is constant, the current will be constant. Now, a couple of things that we can point out here. When we plug into an outlet, the outlets are designed to produce, on average, 120 volts. Now, the peak voltage is actually larger from that by a factor of the square root of 2, which works out to be about 170 volts peak voltage. So when we write out the voltage as a function of time for the generators in our power plant, that can be represented as V naught sine omega t, where omega is an angular frequency. So we saw this back when we were studying oscillation, and we can bring back that angular frequency variable and use that in our formulas for explaining how the voltage is varying. That's going to be in radians per second. Those are standard units. Now, what you may know, what you may be familiar with, is that the outlets our alternating current outlets are designed to operate at 60 hertz. So hertz is not a standard unit, it's cycles per second. When we convert frequency into radians per second, we have to multiply by 2 pi. And so taking the 60 hertz, multiplying by 2 pi, gives us a value of 377 radians per second. So the radians per second value here is 377. So, you could go around to all the appliances that say designed to operate at 60 hertz, and you could cross that out and write in 377 radians per second. Come on, those are standard units. And that goes into our formula here. Frequency, angular... Okay, so the angular frequency standard units radians, frequency F we reserve for cycles. So again, this average voltage is referred to as RMS, and we're going to have to take a look and see what RMS actually means. So let's do that. So here's an AC power supply. Here's a generator, and here's a resistor. So it looks just like what we were looking at before, except instead of operating this off of a battery, we're operating off of the generator. And so what's happening then is that the electrons, instead of consistently being pushed in one direction, and all of the electrons are making their way through the circuit, here the electrons are shifting back and forth. In fact, with the frequencies we operate at, with a frequency of 60 hertz, 60 cycles per second, that's oscillating back and forth 60 times a second. So the electrons are only pushed in one direction for a tiny fraction of a second, and then they're pushed back the other direction. How far do the electrons actually travel? We'll take a look at that later in this chapter, but it's not very far. So when we're operating off AC, which is what we operate with for everything that plugs into an outlet, those electrons are just being oscillated back and forth. The electrons are not traveling very far. But it's still a way to transfer energy from the power plants, possibly hundreds of miles through the grid to where the users are located. So when I plug something in, the energy is coming from a power plant far, far away, but it's still causing the electrons in my device to oscillate back and forth. And if I can get electrons oscillating back and forth in this resistor, that resistor is going to heat up. Okay, so I'm going to be able to transfer the energy into that resistor. So let's see, what can we write down to describe what's going on with AC power? First of all, there's what's called peak voltage, peak current, and peak power. So the voltage that's being generated by the power plant oscillates between a peak voltage in two different directions, and that's represented with a sine function. So V naught, that's the peak voltage, times sine omega t keeps track of that process. Now the current, as a function of time, is going to be V divided by R. So I can take this, divide it through by the resistance, and that gives me I naught. So I naught is equal to V naught divided by R, and it will have the same sine function. It will have the same sine of omega t factor combined onto that. Now, if I calculate the power, the way I'm going to calculate the power is to take the voltage times the current, and I can take that as an instantaneous formula. So the voltage is varying. As a result, the current is varying. And so I can take these two functions, this one and this one, can multiply them together, and the power as a function of time becomes V naught I naught times the sine squared of omega t. I'm going to pick up a factor of sine omega t here and a factor of sine omega t here. So I'm going to get two factors of sine omega t from that. Now, what I'm going to introduce then is P naught, a peak power, where the peak power is equal to the voltage peak times the current peak. So I'm taking all the peak values, and I can graph that also. So here is power as a function of time. Now, on these graphs also, I've introduced one period. Now, if the frequency of oscillation here is 60 cycles per second, then the period of one of those oscillations would be 1/60th of a second. The way we generate that is that the generators back in the power plants, again, it's a bunch of wires that are spinning through magnetic fields. Those are going to be spinning at 60 cycles per second. And so if we make sure that whatever is driving the generators, this could be a hydroelectric plant, it could be a natural gas turbine, whatever is spinning those generators is going to be spinning them at 60 cycles per second. And so the time scale, that's one cycle, that's 1/60th of a second. Here is one cycle of current, that's also 1/60th. But when I multiply these functions together, notice that the voltage and current alternate in directions, but the power that we get doesn't depend on the direction. If I take this voltage times this current, I get a positive value for the power. If I take this voltage times this current, I also get a positive value. So for every cycle of voltage and current, I'm going to get two power cycles. So during that 1/60th of a second, I'll hit peak power twice. Now the power formula is P naught times the sine squared of omega t, and it's pretty easy to determine what the average power is. If I've got something plugged into an AC outlet, the average power is going to be 1/2 of the peak power. So I can take that value of peak power and I can take 1/2 of it, and that's going to determine what the average is. So, and there it is. So the average power is equal to the peak power times 1/2. And when I look at appliances, they're rated in terms of their average power. So if I see a toaster and it says it's 800 watts, that 800 watts is an average power. The peak power would be twice as much. The peak power would be 1600 watts. And so the idea is we want to be able to have an average power so that we can quickly do energy calculations. All right, now if I'm going to average the power, I also should go back and average the voltages and the currents. So here is the formula that I want to be able to use. I want to be able to say the average power is an average voltage and an average current. Now, if I just average the voltage of the current, I'm going to get 0. I can't just do a straight average. The voltages and the currents actually reverse direction. So what we do instead is we do what's called an RMS calculation. And we did this back in thermodynamics, if you remember. In thermodynamics, we did root mean squared calculations for velocities of gas molecules. And so we're going to do the same thing here. What we have is we have a product of voltage and current. And so if I assign a factor of the square root of 1/2 to the voltage and the square root of 1/2 to the current, I can define what we call RMS, or averaged currents, and RMS voltages, which are averaged voltages. Now, the VRMS and the IRMS are defined in a way where the average power is the product of the RMS values. So again, if I buy an appliance and I'm looking at the voltages, or if I'm looking at the current ratings, those are going to be RMS values. That's the convention, is to work in terms of these RMS and average values, because that's going to tell me the quickest way to determine how much energy usage these devices are going to have. All right, so that's a lot of important stuff for AC power. So for figuring out the rate at which energy is being provided from an AC power source. Okay, so let's go back and look at a battery. So let's try this. Here is our electric battery. This is maybe kind of a simplest type of battery. If we just have a couple of metal electrodes, this one has zinc, and this one has carbon, in sulfuric acid. Now, you know when you buy a battery in a store, the reagents inside are running a different reaction than this. The batteries you buy in the store aren't filled with a solution of sulfuric acid. There are other reagents inside there that are operating that battery. Okay, so here's a flashlight battery, and here's the carbon electrode here, and here is the zinc cup, and here's this electrolyte paste, they say, in between. So this is more familiar type of battery that we actually operate from. Okay, let's get back to the electric current definitions here. So current is defined as charge per time, and we can take that right into derivative form. So we can take that into differential forms, dq divided by dt, as needed for our calculations. So here's an example. Let's get in and try doing some calculations with these. So it says this. It says that we have a circuit set up, and there is a steady current of electricity, of electrons, at a current of 2.5 amps. And the wire has, for 4 minutes. So it's flowing through a wire, and that goes on for 4 minutes. How much charge goes by if that's the case? And how many electrons would this correspond to? So perfect, we can go in and calculate how much charge has gone by. So we could write down this in terms of differentials, dq and dt, or we could go back and say, this is a nice steady current. Let's just, since it's a constant current that we're working with, let's just say I is equal to Q divided by T. And so if the current is 2.5 amps, what that's really telling me is that's 2.50 coulombs going by every second. Here is my circuit. So, here's someone down here doing the measurements, here's someone up here doing the measurements. Because it's one loop, the current here is going to be the same as the current here. And so we can measure the flow rate at any location within this one loop. If the charge is going by at a rate of 2.50 coulombs every second, and if we allow that circuit to operate for 4 minutes, now minutes aren't standard units, so we've converted those over into 240 seconds, and yes, that's a 4. Okay, a little suspect, but that's a 4. Oh, you can see it down here. That 4 is a little more distinct. So we want to find out how much charge has gone by. So it's going by at a rate of 2.50 coulombs per second, and we allow this to go on for 240 seconds. If we just multiply those numbers together, we end up with 600 coulombs of charge. Okay, so I'm going to end up with 600 coulombs of charge that have passed by this location. Now, if it's 600 coulombs of charge, how many electrons is that? So let's think about that this way. A certain amount of charge is equal to some number of electron charges. Now, the fundamental electron charge is 1.60 10 to the minus 19 coulombs. So each electron has that much charge. So let's take the 600 coulombs and say for every 1.60 10 to the minus 19 coulombs, that is one electron. And so the number that I'm ending up with here is, it's a big number, 3.75 times 10 to the 21. So now that's less than a mole. That's about 1/100th of a mole. 2 amps, that's a pretty good size current running through the wires. And we did let it go by for 4 minutes. Okay, but we can go in and actually count the number of electrons that pass a certain location. So if I stand here and count the electrons going by, I'm going to get that number, 3.75 10 to the 21 during that 4 minutes. If I stand here and do the counting, I'm going to get the same number basically. All right, let's get back to a couple of the formulas that we had looked at. First of all, we said that the current is determined by the voltage divided by the resistance. And so I can flip that around and say the voltage is the current times the resistance. And then let's see how that gets used in some of our calculations. So it says that, and this is pointing out that if I take that formula, if I take the current and say that it's equal to V over R, then what happens is, if I plot that, if I increase the voltage operating through that resistor, through that resistance device, what's going to happen is as the voltage goes up, the current will go up, and it will give me a linear plot. So this is referred to as Ohm's law. Ohm's law says that the amount of current we get is directly proportional to the voltage. Now that describes many, many devices, but it doesn't describe all devices. Some materials behave differently, and so semiconductors, for example, materials like silicon, don't follow Ohm's law. Instead, what happens is the voltage goes up at first, the current goes up slowly, but then it rises more rapidly. So there are materials that don't follow this nice linear relationship, and they're more complicated to go in and analyze. For our purposes right now, we're going to be sticking with devices that do follow the simple formula for the most part. We're going to be looking at devices that behave this way. All right, here is a resistor. It's part of a circuit, and here is point A and here is point B, and I can take a voltmeter and I can place it across. So there's a couple measurements we can do here. I can get a voltmeter and measure what the voltage differences are. And what I can also do is I can get what's called an ammeter, and I can measure the flow rate. So I have ways to go in and measure the voltage across the resistor. And that's an important phrase right there, the voltage across the resistor. What's the difference in electrical potential between point A and point B? The current is flowing through the resistor. So to measure the current, we can bring out an ammeter that actually is able to determine at what rate charges are flowing by. So on this example, it says, which of these locations would be at a higher electric potential? So we have to make an important determination here. We've got to go back and let's go back a little ways here. Let me go all the way back to, you guys remember that very first diagram? There we go. So here's a battery, and here are all these electrons. I think this is the best reference to work from. This is the direction that the electrons are being pumped, and everything we've talked about up until now works, except the current is defined to be going in the opposite direction of the electrons. At the time that electric current was defined, you know, back in Benjamin Franklin's time or whatever, we didn't know what the charge carriers were. We didn't know that there were these little particles called electrons, and we didn't know that they were the ones that were negatively charged, and we didn't know that those were the ones going through the wires. And so it was kind of a coin toss, and researchers defined current to be in the direction from the positive terminal to the negative terminal. So historically, we're left with this kind of, well, it's not so much, it's not too difficult to work with, but we have defined current to be opposite the flow direction of the electrons. Now, not every example of current is based on electrons. If we have a solution with different ions in the solution moving back and forth, we can define current also in terms of positive ions, for example. But the most common example of electric current is through some wiring, and so we just have to remember that the current got defined to be in the opposite direction. Now, where does that actually become important for us? And catching up here, back to where we are. Okay, so what's happening here is that the current is going in that direction, but that means the electrons are actually going the other way. Current is defined in a direction as if the charges that are moving are positively charged, not negatively charged. And so that says that point A is at a higher electric potential than point B. So the voltage drops in going from point A to point B. So we'll say that there's a voltage drop or a voltage across the resistor, and point A is going to be the higher voltage and point B is going to be the lower voltage. If I get a voltmeter out and I measure the voltage between A and B, and it reads positive 3.5 volts, if I take the leads from that voltmeter and reverse them, it will now say minus 3.5. So my voltmeter can tell which is relatively at the higher voltage and which one relatively is at the lower value. So it can determine the orientation of a voltage drop. Something to be aware of as we look at more circuits. So here's a flashlight. And it says that we have a 1.5 volt battery, and the flashlight uses, now this is other vocabulary that gets used, it says that it's drawing 300 milliamps, so those are 300 thousandths of an amp from the 1.5 volt battery. So what's the resistance of the bulb? And I think we should calculate the power too. So let's go in and do a couple of calculations here. So in this example, what we've got is we have the 1.5 volt battery, and we're observing that we have 300 milliamps of current going through the battery. So this is given, 1.5 volts, 300 milliamps. From that, I can use my formulas to determine what the R value is. So the light bulb, oh look, I put a switch in, finally. So the resistance can be calculated by taking that voltage, dividing through by the current, and that says that my resistor, the light bulb, is 5 ohms. And I think the symbol here is the Greek letter omega. Isn't that clever? And so for representing the unit of ohms, which is named after somebody, we use the Greek letter omega. So anyway, we have a bulb that's 5 ohms. Now, how much power? We didn't calculate power. Power would be V times I. And so that would be 0.45 watts. Anyway, moving on. Now in part B, they say same flashlight, same light bulb, and that means that the light bulb is still 5 ohms. I haven't changed the design of my light bulb. It's still operating at 5 ohms of resistance. But it says the battery is kind of getting worn down, the reagents are becoming depleted, and that it's only maintaining 1.2 volts. So if the voltage actually drops to 1.2, how much current will we have? And for that, I can go back and flip my formulas around. Current will be given by V over R. That's going to give me 0.240 amps or 240 milliamps. So where we used to be producing 300 milliamps, the current now has dropped to 240. Also, what used to be 1.5 volts is down to 1.2. If I take the 1.2 and multiply by the 240, we'll see that the power has dropped. It's like a 20% drop in voltage, 20% drop. It's going to drop by like 30% or something, right? So we're going to see a fairly significant drop in the power of that flashlight. And you guys have experienced that when the flashlight batteries begin to go. All right, here is a picture of what a resistor, kind of what a resistor looks like. And so it has these different color bands on here. It's got one significant figure, two significant figures. So it's got two significant figures. And then it has a multiplier. So let's say that, what is red? Red is like 1, and green is like, I don't know, maybe this is 1 and this is 5, and the multiplier is 1,000. Well, that would be 15,000 ohms. And the tolerance depends on this last band of, it's like silver or gold or something like that. So they put different colors on these. Rather than trying to label them with little tiny numbers, they put these color bands, and then you have to have good color vision to be able to look at a resistor and figure out how much resistance it has. Oh, here we go. Let's see, red is 2, green is 5, so that was 2 times 5. What was the color on that multiplier band? The multiplier band looks like it's yellow. At least that's my ooh, that's 10,000. So 25 times 10,000 is 250,000. That's a lot of ohms. And then the last one says how reliable it is. Now ours had a silver band, and a silver band says that this resistor is reliable to within 10% of the stated value. All right. Some clarifications. I think we've talked about these. Let's see. Batteries maintain, we're going to treat them as a constant voltage. So the batteries are maintaining pretty constant voltage. Resistance is a property of the material. Resistance property of the material. That's not true. It's resistivity is the property of the material that it's made out of. Resistance is the device itself once it's been completed. So there's resistivity, which is the basic material property, and then there's resistance. Current is not a vector, even though it has a direction, so current's just a number. Current and charge do not get used up. Electric charge is conserved. Whatever the count is of electrons going through a circuit, we'll be able to account for all those electrons at every location. So they don't get used up. Now, a battery, the chemical reagents, once those chemical reactions have run, then we run out of chemical reagents and the battery no longer operates. But current, the actual number of electrons in the device and the rate at which they're flowing, that doesn't go away. The current has to be able to be accounted for through these closed loops inside a circuit. So here is resistivity. Let's get back. We saw this formula earlier. We said that the resistance of a device depends on what it's made out of, which is the resistivity, times the length divided by the cross-sectional area. Okay, and here's some examples of resistivities of different materials. So let's see, some of the very best conductors, silver, copper, and gold. Silver is actually, a better conductor than copper, which is better than gold. And then as we move down here, aluminum has been used for wiring. So aluminum's value is pretty low. And then we have a bit of a jump to tungsten, iron, platinum. Ooh, and then platinum and mercury, the resistivity has gone up a lot. So platinum's actually quite a bit higher in terms of resistivity. Anyway, that's a materials property table. Now what we also find is that for metals, the resistivity goes up with temperature. So these are determined at standard temperatures, probably 20 Celsius. Yeah, 20 Celsius. So the values we have here are the standard values. If we're operating at a higher temperature, we have to account for that using the temperature coefficient. If we're operating at a lower temperature also, then there'll be a reduction in the resistivity, and we can account for that also. Here are some speaker wires. Here's an example where we've got some, here is a sound system driving some speakers. We've got 20 meters of wire running out to these speakers that we've placed. It says you want to take your stereo and connect it to some remote speakers. It says each wire is 20 meters long. What diameter of copper wire should you use to make sure that the resistance is no larger than 1/10 of an ohm? So the idea is this. The idea with most appliances is that we want to minimize the resistance in the wiring. The wires could run for a long distance through, well, think of a power plant, right? We've got a power plant that could be hundreds of miles away, and we have to be able to have the electricity operate all the way in the wires from the power plant all the way to where we're utilizing that. We have to make sure that that total resistance in getting here is actually pretty small compared with the resistance inside of our devices. And so we have to make sure that the wires are thick enough that they will provide very low resistance. So again, here's a battery. Here are two resistors, the resistance in the wiring itself, and then here is the resistance in the speaker, the device that we're trying to provide power to. And so what we can do here is, let me check the numbers. This is saying 4 amps. Is that what they said? Yeah. So it says each speaker is going to get 4 amps. Okay. So let's see if we can. So I'm just going to look at one of the speakers, and we want to make sure that we continue to have 4 amps cycling through this circuit. And I'm going to treat this as a battery. I'm not going to deal with AC, alternating current. Let's just work from a battery. Now, it would work the same way if we were plugging this into an AC source. It's just that the voltages would now be RMS and the currents would be RMS. So here is what the resistance is going to be determined by. We've got 20 meters of length. It says that we want the wires to have no more than 1/10 of an ohm. And we're going to make this out of copper, so there's the resistivity. So we can take the formula that we were just looking at, the formula that says, let's use this formula and solve for the cross-sectional area to determine how much, to find out how much diameter, what diameter wire we want to be able to use. So taking that formula, solving for the cross-sectional area, putting all these numbers in, I ended up with 3.3. Now, I'm a little concerned about this 20 meter. The 20 meters was, I bet I was supposed to double that, and I didn't do it. Okay, so it said 0.1 ohm per wire. So I'm not quite sure. In any case, this is the numbers I've used. So in the 20 meters of length, I'm going to say there's 1/10 of an ohm here. And then, of course, the speaker is connected with 2 of those wires, and each one will have 1/10 of an ohm. Let's see. And so solving for the cross-sectional area, we get this, 10 to the minus 6. And then the area, let's say that the copper wire has a circular cross-section, I can solve for r. So r will be area over pi square root, and that gives me 1.03 10 to the minus 3. Oh, that looks like about a millimeter of radius. So that would be about 2 millimeters of diameter. So that's not bad. If I get a copper wire, it's 20 meters in length, you know, that's like 65 feet or something in length, and it's a couple millimeters in diameter, so it's not too thick, but that's going to provide only 1/10 of an ohm of resistance. So that's pretty good. So we're actually able to keep the resistance pretty low. Now, if I'm looking at the voltage loss along the wire itself, so when I look at the voltage here, some of that voltage is going to get used up in the wiring. The wiring will heat up, and some of that voltage will get used by the speaker. So I want most of the voltage to be available to the speaker. How much of a voltage drop will we have along the 20 meters of wire? And so for each 20 meter length, I can calculate the voltage loss specifically across the wiring and its resistance as R times I. And that says that the voltage loss will be 0.4 volts. Now, if I'm operating at 120 volts, and I'm only losing 0.4, that sounds pretty good. So that's the way we would run the numbers and find out, is the wiring, are we going to end up using a lot of our energy in the wiring, or is most of the energy going to reach the speakers? And it sounds like with the setup we've got, with the numbers we were given, most of that energy is going to reach the speakers. Okay, here is the resistivity as a function of temperature. As the temperature rises above our reference temperature of 20 Celsius, the resistivity goes up. I can plug in an alpha, I can plug in the standard resistivity value, and I can calculate how much the resistance is going to be. So that's just a formula we can plug into. Now, electric power, we had shown that the electric power can be determined in an electric circuit by I times V. So I need to know what the current is, and then I need to know what the voltage is going to be. The unit of electric power is the watt. So same as it is for any other system where we're looking at power. And so the power then can be written as I times V, or V times I. And then if I take the V and substitute in I times R, that's going to be R times I squared. So power could be written as IV. It could be written as I squared times R. It could be written as V squared over R. Any of those will work. So better check time here. And yeah, it's time for a break. So let's do that. If you guys have any questions, let me know. But let's go ahead and take a break for 10 minutes or so, and then we'll pick back up.